So we were talking about the ability of our classifiers to generalize and the need to have training sets and testing sets. And we left off talking about cross-validation. And cross-validation, this is basically a technique for using the same data points both for training and for testing, just not at the same time. And the reason you do that is to use as many data points in your testing set as possible. You want to do that because many large testing sets lead to tight confidence intervals on the error rate, but at the same time you want your training set to be large so you can train a reasonably good classifier or regression system. So remember, the idea there was we're going to take our data set, we're going to split it up randomly into, say, 5 different parts. We're going to take one of these parts, use it as a testing set, and use the other 4 to train the classifier, test it on this portion, and then move along to the next fold, right? Train it on 4 of the subsets and testing it on the subset 2. You repeat it 5 times. By the end of it, you have used every data point as a testing instance, and you can put them all together and compute an accuracy or an error rate based on all of those instances. So you're using 100% of your data as testing data, so your estimate of the error is as accurate as it could be. You're also using 80% of the data to train the classifier every time, which is pretty good. And if you do tenfold cross-validation, then you're using 90% of the data every time. So if you take this reasoning to a limit, you get something called Leave-one-out, which is basically n-fold cross-validation, where n is the number of instances in your data set. So if I have 1,000 examples, I'm going to use 999 as training set and test it on 1 remaining instance, and then I'm going to take another instance, train on 999 and test on that 1 instance, repeat it 1,000 times, and that seems really, really attractive. Why? Because it's cross-validation, it's fair game. I am using every single instance as a testing point, and I'm also using almost the entire data set for training. So I should be confident that I've learned the best classifier that I could possibly learn on this data set. So this should be a really, really good example, a really, really good estimate of the generalization error. Right? There are a couple of downsides. One downside is the high computational cost. Effectively, what you're going to be doing is, if you have a data set with 1 million entries, you're going to be retraining your classifier 1 million times over. So you retrain it, you test it on 1 point that was left out, and you retrain it again 1 million times, very computationally expensive. Now, it's not a problem for some methods. For example, we're going to be talking about nearest neighbor methods. They do this thing anyway, right? So for nearest neighbor method, it's not a problem to do Leave-one-out. And for other classifiers, there are tricks that make learning a little bit more efficient, so you don't have to relearn from scratch. So it is a problem, but it's not a huge problem. There's a bigger problem, though. And the problem is, when you do Leave-one-out, the balance of classes in your training and testing portions is drastically different. And this can cause really serious problems. So let's look at one very specific example. Suppose I have data with no attributes. Right? No attributes, none. I have nothing to base my predictions on. And I have 2 classes, maybe ham and spam, positives and negatives, and they're equiprobable. So half the examples are positive, half the examples are negative. What error rate am I supposed to get? What is the expected error rate of the best possible classifier on this data? 50%, right? So whatever I do, I should be getting getting it right half the time and wrong half the time. Because it's 50-50 split, I can't use the majority. Now, what would be, in the absence of any attributes, what do you use to classify? What is the simplest classifier that you use? I'm sorry? Yeah, you could flip a coin, but in general, flipping a coin is completely random. So what is the next best thing? Yes, you always predict 1 class. And which class would you predict? Not in this case, so forget about the equiprobable, just in general. The most frequent class, right? because that is going to minimize the error rate. You're going to be correct as often as possible if you predict the most frequent class first. And when you have no attributes, the majority rule, the most frequent class, that's your best possible classifier that you can come up with. Okay? And you would expect that classifier to have a 50% error rate in this particular case. The problem is if you do it live one out, you're actually going to be wrong 100% of the time. So your estimate for the error rate is going to be 100 instead of 50. Why is that? It's perfectly balanced until I do leave one out. And when I do leave one out, think about what's happening. I have two classes, A and B, right? I'm going to have only one instance in the testing set, and let's say that instance is of class A. So in my testing set, I'm going to have one example of A and 0 examples of B. And what about my training set? My training set is going to have half of B and half of A, except I've taken one A away, right? So my training set is now biased towards class B. So my majority classifier is going to say B, right? Because B is just a tiny little bit more likely than A, and the majority rule holds, so you're going to classify it as B. And of course, you're going to be wrong. And you're going to be wrong on every single instance. So if you do leave one out with a majority classifier, yeah, you're going to be wrong 100% of the time in this particular case. And you can come up with other pathological examples where leave one out leads to really strange behaviors.